Hello, we're solving 9701 May-June 2022, paper 1-3 today. Starting from this year, we have 1 hour 15 minutes, and section B has been removed, alright? So, we only have single best answer questions, 40 of those, and you no longer have access to the data booklet, alright? But you will be given the periodic table at the end of the booklet. So, that's all. So, I'll be solving paper 2 after this, when I'm done with this series, and physics and bio. So let's see. Let's look at the threshold. This is paper 1-3. The maximum mark was 40, right? 40 MCQs. So A was at 24, B was at 21, C was at 17, D was at 14, and E was at 11. So this was identical to paper 1-2. And A star should approximately be at around 30 marks. It's not mentioned in the mark scheme, I mean in the threshold, but it should be around that mark, okay? Alright, let's begin. Which atom has exactly 3 unpaired electrons in the ground state? Okay, wait, let me bring the periodic table. So, an isolated aluminium atom. We need 3 unpaired electrons. For aluminium, basically it's 1s2, 2s2, 2p6, 3s2, 3p1. The 3s2 orbital is full, and one of the 3p orbitals has 1 electron. So that's 1 unpaired electron only, understood? So it's not aluminium. It's probably going to be phosphorus or nitrogen. Someone in group 15, basically. That's that. So carbon. If you go to carbon, what about carbon? Carbon is 1s2, 2s2, 2p2. So it has 2 unpaired electrons. So carbon is excluded. Aluminum is excluded. What about chromium? Chromium is over here. Chromium was supposed to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4, but this is an unstable state, right? As a result, it's going to be 4s1, 3d5. So chromium actually has 6 unpaired electrons, 1 in the 4s orbital and 5 in the 3d orbital. Okay, so it's too much. What about phosphorus though, our last option, right? Phosphorus, it's 1s2, 2s2, 2p6, 3s2, 3p3. So for phosphorus in the 3p orbital, we have 3 unpaired electrons. So I'm going to go with phosphorus, right? So 1 is actually C. Moving on. Which element has the second smallest atomic radius in its group and the second highest electrical conductivity in its period? Interesting. So we're talking about period 3 over here for sodium and magnesium. So I circled the wrong answer, right? It should be D. Phosphorus is the correct answer. Which element has the second smallest atomic radius in its group and the second highest electrical conductivity? Okay. second smallest atomic radius. As we go across the period from left to right, atomic radius decreases. So it can't be sodium. Okay, it can't be sodium because, oh, we're talking about the group, right? Okay, so we're talking about groups. So if we're talking about group 2, group 1, for group 2, magnesium has the, okay, beryllium has the smallest atomic radius followed by magnesium. So magnesium has the second smallest atomic radius that fits the criteria. Also, let's talk about electrical conductivity across the period, right? Across the period, the electrical conductivity is like this. This is sodium, magnesium increases. Okay, sodium, magnesium, aluminum is higher. Then silicon decreases, but not much. It's a semiconductor, right? Followed by the other ones, the non-metals. They're close to zero. So yeah, magnesium actually has the second highest electrical conductivity. Aluminum has the highest, magnesium has the second highest. So I'm going to go with magnesium. It can't be sodium because it has the third highest conductivity. Okay, so it's not sodium. It can't be calcium because calcium is not the second smallest in the group. And it can't be boron because boron has much less electrical conductivity. Okay, and we're not supposed to know the trend for period 2. Okay, so period 2 and 4 were already excluded in the first place. It was between sodium and magnesium. All right. The ideal answer is magnesium. Number 3. Analysis of the hormone thyroxine gives the results shown. Heating 0.5 grams of thyroxine with aqueous silver nitrate produces 0.604 grams of silver iodide. All of the iodine in the thyroxine sample is converted to silver iodide. Complete combustion produces 232 cm3 of carbon dioxide and 7.72 cm3 of nitrogen. Which molecular formula of thyroxine agrees with these values? Okay, let's start with A. Trial and error. C15H11NO4I4 reacts with silver nitrate to form silver iodide. Okay, so this has to be 4, this has to be 4 as well. So the MR of this compound is 776.6. So 0.5 by 776.6 gives us a value of 6.43 into 10 to the power minus 3. So if you do the molar ratio correctly, it will be 4 times this value for silver iodide. So this into 4 is basically 2.575 into 10 power minus 3. That's the moles of silver iodide. Now if you multiply this by the mass of silver iodide, which is, sorry, the MR of silver iodide, iodide is 126.9 and silver is 107.9. So into 107.9 plus 126.9, that gives you a value of 0.604. I'm getting a value of 0.604 grams. So that matches actually. The mass matches. Now let's go to combustion. Let's see if combustion is alright. So we have C15 H11 NO4I4. When it reacts with excess oxygen, we get carbon dioxide and nitrogen. So carbon dioxide should be multiplied with the 15. What about nitrogen? Since there's only one N over here, since there's only one nitrogen, we should put a half behind this, right? So we had 0.5 grams of this, or 6.43 into 10 to the power minus 3 moles of this. So how many moles of gas do we have in total? 15 plus 0.5, 15.5 moles of gas. Okay, but we need the moles individually. So 15 moles of carbon dioxide. So how many moles of carbon dioxide do you get from this? 15 times 6.43 into 10 to the power minus 3 gives us an answer of 0.09645 moles of carbon dioxide. If you multiply that by 24,000, wait, so 0.5 divided by 776.6, 6.43 into 10 to the power minus 4. Sorry, I made a mistake over here. It was actually minus 4 over here, okay? Times 4. And then times, that one was 2.57 into 10 per minus 3. This is okay, right? But the moles for that compound was wrong. Okay. So yeah, back to this. 6.43 into 10 to the power minus 4 moles of our compound over here, thyroxine. So if you multiply that with 15, you're getting this answer. 9.66 into 10 to the power minus 3. Now, since you have 15 moles of carbon dioxide, I multiplied that value with 15, 6.43 into 10 power minus 4 into 15. Now, if I multiply this with 24,000 cm cube, we're going to get the answer. I'm getting 232 cm cube. So that matches. And you can check nitrogen. That should be done in this way. Basically, 6.43 into 10 to the power minus 4. Okay, 6.43 into 10 power minus 4 into 0.5, which gives us a value of 3.215 into 10 power minus 4 times 24,000, which gives us a value of 7.716. Okay, which is 7.72 cm cube. So luckily, our answer is A. I'm not testing the other ones. Okay, so it matched with this. 4. How many moles of oxygen are needed to burn 1 mole of ethane if the products of the reaction are water and carbon only, incomplete combustion? Okay, so ethane, we have CH4, CH3, CH3, ethane, plus oxygen gives us carbon and water only. So we need 2 moles of carbon and 3 moles of water. And so we need 3 by 2 moles of oxygen. Okay, so 4 is logically A. Which compound has the smallest difference in electronegativity between the two elements? Fluorine has the highest electronegativity. Okay, so the difference will be wider. So it can't be A or C. It needs to be bromine, because as you go down the group, electronegativity decreases. What about potassium and lithium? What about potassium and lithium? It can't be fluorine because it has the highest electronegativity. Bromine has lower electronegativity. And if you compare potassium and lithium, potassium has lower electronegativity. Okay, but here's the thing. Suppose the electronegativity of fluorine is 4. This is true. Bromine might be around 3, maybe it is around 3. So for lithium, it might be around, for NaCl, the difference is around 2. It's around 2. Approximately around 2, right? So if you go down, for potassium, it should be around, it should be less, maybe 1.5. So if you want the smallest difference, what should you do? You should take, like, you have two ends, right? The upper bound and the lower bound. you should actually increase your lower bound and decrease your upper bound. So I decrease my upper bound, bromine, and I should increase my lower bound, so I should take lithium because it has higher electronegativity. So I'm going to go for lithium bromide, and it should be correct, and the correct answer is D. This was a tricky one. All right, test your skill. Next, VSE PR theory should be used to answer this question. Hydrogen has the following structure. What is the predicted bond angle? So this nitrogen is sp3 hybridized, but it has one lone pair. As a result, it should have been, for 4 bond pairs it's 109.5, but due to the increased repulsion, it decreases by a bit and it becomes decreased to 107 degrees. Next, 7. This question is about the buckyball, Buckminster fluorine, graphite, iodine, and diamond. How many of these are simple molecular? So I'm going to tell you something interesting. I actually lost my 1 mark in my AS chemistry exam because I didn't know that the buckyball was simple molecular. I was confused back then, but it was mentioned in the syllabus. So always go through the syllabus before giving your exam. It's really important. So the buckyball is actually simple molecular. Iodine is simple molecular, but graphite and diamond are not. So I'm going to go with 2. 8. A student reacts 1 mole of magnesium powder in a sealed 0.030 meter cube container of oxygen at a pressure of 2 into 10 power 5 pascals and a temperature of 600 Kelvin. The magnesium reacts completely to form magnesium oxide. Which percentage of oxygen will be used up? Okay. PV is equal to nRT. 2 into 10 power 5 into 0.030 is equal to 1 into 8.31 into 600. Okay, wait. 1 is the moles of magnesium powder, so we can't use 1. We're going to use N. Let's find out N. 2 into 10 power 5 into 0.03 divided by 8.31 divided by 600 gives us an answer of N is equal to 1.2. We have 1.2 moles of oxygen. Now here's the thing. We have magnesium powder which reacts with oxygen, this moles of oxygen 1.2, to form MgO. What is the molar ratio actually? We need, the molar ratio is 1 is to half. So if we have 1 mole of magnesium, how much do we need? We need 0.5 moles of oxygen gas, and we had 1.2 initially. So if we subtract 1.5 from 1.2, we still have 0.7 oxygen moles of oxygen remaining. So what percentage of oxygen will be used up? Okay, so 0.5 out of 1.2 was used up, right? 0.5 out of 1.2 was used up. So actually 41.6%, 67% was used up. So 42% was used up basically. So 8 is C, all right? 9. Which equation represents an enthalpy change, that is the average bond energy of the CH bond in methane? Okay, so this one over here, 9C, this actually represents, when you break this up to C plus 4H, you're getting the bond energy for 4 of these. That's why C is not the answer. What if we just multiplied 1 by 4 here? Then we'd actually end up with the bond energy for CH, right? That is exactly why the answer is B. And remember, bond energy is always represented in bond breaking, not bond making. That's why we didn't opt for A. And why not D? This is bond making, these other 3 are bond breaking. Why not D? Because in D, we only break 1 bond. That is not the average bond energy though. To get the average bond energy, what do we need to do? We need to break all 4 and then divide by 4. Then we're gonna get the average, right? That's how average works. Interesting question. 10. Magnesium carbonate decomposes when heated in a Bunsen burner flame. Values for the standard enthalpies of formation of the species involved are shown. Formation of magnesium carbonate is this. Okay. Decomposition of magnesium carbonate. So MgCO3 is broken down to form MgO plus CO2. So for formation, remember the arrows will go upwards, and we need the elements at the bottom. Okay, here you go. So we have a direct route or the detour. We need to find out this del H. So for formation of MgCO3, it's minus 1095.8, and for formation of magnesium oxide, it's minus 601.7 and minus 393.5. Okay, so we can say that del H plus minus 1095.8 is equal to minus 601.7 plus minus 393.5. There you go. So if you solve this, minus 601.7 minus 393.5 plus 1095.8 gives us an answer of 100.6. Alright, so I'm going to go with 10A. 100.6, that's that. 11. Ammonium nitrate decomposes into N2O and H2O on heating. So we need a 2 over here, and everything else is balanced. Yeah, all good. The ammonium ion is behaving as a reducing agent. Nitrate ion is behaving as an oxidizing agent. It is a redox reaction. Okay, let's check. So we are breaking this down with the help of heat. Here in ammonium, the oxidation number, this is plus 4, this is minus 3. So ammonium has a charge of plus 1. And in nitrate, it has a charge of minus 1, right? So oxygen is minus 6 and nitrogen is plus 5. The oxygen is minus 6 and nitrogen is plus 5. So what is happening here exactly? The oxidation number of nitrogen is changing from minus 3 and in ammonium, and the oxidation of number of nitrogen in nitrate is also changing. What are they turning into? This is minus 2, right? So nitrogens combined should have plus 2. So each nitrogen has an oxidation number of plus 1. So it's actually going from plus 5 to plus 1. It is being reduced, and similarly at the same time it's going from minus 3 to plus 1. It's being oxidized. So the nitrogen in ammonium is being oxidized and the nitrogen in nitrate is being reduced. Okay, so since ammonium is being oxidized, remember the species which gets oxidized behaves as the reducing agent. Since ammonium is being oxidized, it is reducing nitrate. So 1 is correct. And since nitrate is being reduced, it is oxidizing ammonium. So it is acting as an oxidizing agent. So 1 and 2 are correct. Now what about 3 and 4? This is a redox reaction, I agree. What about 4 though? It is a disproportionation reaction. This is wrong. This is wrong. 11 is B. I'll tell you why though. For disproportionation reaction, the same species has to get oxidized and reduced at the same time. But this is not the same species. It is the same nitrogen element, but these are different nitrogens because they have different oxidation states. Do you want an example of a disproportionate reaction? Suppose chlorine plus cold NOH is NaClO plus NaCl plus H2O. Get it? So yeah, this same chlorine, which was at an oxidation number of 0, turned into plus 1 and minus 1. The same chlorine did that. That's why it's a disproportionation reaction, okay? Alright, so for 20, student adds 3 moles of acidified potassium dichromate to an excess of iodide ions, alright? The chromium is reduced to Cr3 plus and iodide ions are oxidized to I2 plus. I2. The I2 released is reduced back to iodide ions by X moles of thiosulfate. Ions. 1 mole of iodine is reduced by 2 moles of thiosulfate. What is the value of X? Okay. Let's see. So we basically have Cr2O7, 2 minus. It reacts with an excess of iodide. The chromium is reduced to Cr3 plus. We have H plus as well. This solution needs to be acidified or it won't work. And the iodide is converted to iodine. So iodide goes from -1 to 0. But since there are two iodine atoms in one molecule, the change should be 2. What about dichromate? Dichromate goes from, this is a -14, so this is +12. So each chromium ion has a charge of +6, goes from +6 to +3. So for each chromium ion, the change is +3. So for two chromium ions, the change should be 6 in total. Okay, the change is 6. So how are we going to balance this change? 6 and 2. How are you going to balance 6 and 2? Basically, you need to multiply this 2 with 3. Then you're going to end up with 6. So we need um, 3 iodine molecules or 6 iodine atoms in total. All right, then everything should be all good. So we need 3 iodine molecules or 6 iodine atoms. The total change will be 6 electrons. And for chromium, it was 6 electrons in the first place. That's all. So next, what's going to happen? The next reaction is the iodine is reduced by 2 moles of thiosulfate basically to form iodide. Now the iodine released in that reaction, so basically we had 3 moles of dichromate. Initially we had 3 moles of dichromate. So for 3 moles of dichromate, how many moles of iodine will be released? It will be 3 times that value. So 3 times 3 is 9. So in total, due to 3 moles of acidified dichromate, we got 9 moles of iodine, right? We got 9 moles of iodine in total because this was 3. As a result, if we had 1 mole of dichromate, we'd get 3 moles of iodine, right? So 1 mole of dichromate equals to 3 moles of iodine. So 3 moles of dichromate equals to 3 times 3, 9 moles of iodine. So 9 moles of iodine will react with thiosulfate, basically. So 1 mole of iodine requires 2 moles of thiosulfate. So 9 moles of iodine will require 18 moles of thiosulfate. Does that make sense? So the answer should be D. 12 is D. Tricky sum indeed. Which statement about acids and bases is always correct? An acid with 2 H atoms per molecule will be stronger. No, we never know that because if it might be ethane acid, so it's a weak acid compared to HCl. So 13A is wrong. A concentrated solution of a strong acid will have a lower pH than a dilute solution of a weak acid. This is 100% true. A concentrated solution of a strong base will have a higher pH. This is wrong. A strong acid is more dissociated in solution than a strong base. Wrong. They are equal. They might be equally dissociated because both of them are strong. 14. The reaction between sulfur dioxide and oxygen is reversible. In an equilibrium mixture at 1000 Kelvin, the sulfur trioxide concentration is 6 mol per dm cube. The sulfur dioxide concentration is twice the oxygen concentration. What is the sulfur dioxide concentration? Okay. So this is 6. And if oxygen is X, sulfur dioxide is twice X. Okay. at equilibrium. So the Kc is SO3 whole square O2 SO2 whole square. So that's 6 squared divided by x times twice x whole square. This value is equal to 280, or 280 is equal to 36 divided by 4x cubed. 4x cubed is equal to 36 by 280. So if I solve this, I'm getting an answer of 0.31, 0.318, 0.318. This is the value of x, but they want the value of sulfur dioxide concentration. So concentration of SO2 is actually twice x, which is this into 2, 0.636. It should be D, logically. 14 should be D. 14 is D. Just check the mark scheme. 15. The Boltzmann distribution of the particles in a mixture of gas X and gas Y is shown in diagram 1. X and Y react, and the reaction causes an increase in gas molecules present. The reaction goes to completion. In experiment 1, the increase in volume is measured every 10 seconds. During the reaction, the temperature and pressure remain constant. The increase in volume is shown in the volume time graph. Okay. In experiment 2, the experiment is repeated using identical amounts of x and y. A different temperature is used. Clearly, the Boltzmann distribution has shifted to the left. Do you understand? So, when does this shift to the left? When temperature is decreased. So, compared to experiment 1, temperature is less in experiment 2. The same pressure is used. The Boltzmann distribution is shown. Everything remains constant. But we use the same amount of x and y. So, you got to understand that at the end, the increase in volume will be the same because we have the same amount of reactants. The increase in volume will be the same because we have the same number of reactants. However, what will be different? Since the temperature is lower, more time will be taken to reach that volume. Since temperature is lower, more time will be taken to reach that volume, but the same volume will be reached because we have the same amount of reactants. It's not D because it shows that we don't reach the same volume. A is also wrong because we reach a higher volume. B is wrong because it shows a faster rate. Logically, 15 should be C, but there's a trick over here. Out of these, which curve on the volume time graph would show the increase in volume against time for experiment 2? The origin line is redrawn as a solid line. Okay, so the solid line is actually shown over here, right? We have identical amounts of x and y. The temperature is lower, so the rate should be lower. So for sure A and B are excluded. For sure A and B are excluded because they show that there's a faster rate. It's between C and D. So let's read this again. Increase in gas molecules, the reaction goes to completion. In experiment 1, the increase in volume is measured every 10 seconds. The same pressure is used. The Boltzmann distribution is shown in this diagram. Temperature and pressure remain constant. The answer should logically be C, but the mark scheme answer is D. Because we're using identical amounts of x and y, and the reaction goes to completion. Since we're using identical amounts of x and y, we should get the same increase in volume, because when X and Y increase react, we are getting some other product which ultimately increases the volume. So here it's happening at a certain temperature which is higher than experiment 2. That's why we get it so fast, right? But in the second experiment we should get the same volume but at a greater time. Logically it should be C, because 4D is showing us that the increase in volume is not the same. It's showing us that the increase in volume is much less. But the mark scheme is showing D. D doesn't make sense, guys. Okay, this is I think the mark scheme is wrong. There are sometimes errors printed in the mark scheme. It should be C logically. But if there is a change, if I find a change anytime, or if you guys find a mistake, please let me know. I'm gonna fix that in the comment section. But we can't say for sure until the mark scheme is, the examiner's report is released, alright? It's gonna be available in a few months. Anyway, let's move on. 16. When the temperature of a particular reaction is increased by 10 from 20 to 30, the rate approximately doubles. What is the most significant reason for this? Not a different mechanism, increased collision frequency. But we need to say that these are increased collisions with increased successful collisions. So we can say more collisions that have energy greater than the activation energy. Successful collisions, right? Exactly. This is the answer. A reduced activation energy that applies to catalysts. Which ion has the smallest radius? So basically, if you look at the periodic table, sodium, magnesium, aluminium, and we have barium. Clearly, barium is out of the option because it's so big. So out of sodium, magnesium, and aluminium, all three of them have the same configuration: 1s2, 2s2, 2p6. Understood? But it's just that aluminium has a charge of 3 plus. Aluminium has a charge of 3 plus. So it has greater protons compared to electrons. It has 13 protons but 10 electrons. So the 13 protons can attract the electrons more strongly, which is why it is the smallest cation, 17A. Which was correct? Element with higher fifth ionization energy. Element with amphoteric oxide. Okay, phosphorus has an acidic oxide, so it's either between A and C. Element with higher fifth ionization energy. So the one with the higher fifth ionization energy, logically, if you look at aluminium, the one for aluminium should look like this. Across the period, ionization energy actually increases. So this is the one for aluminium. Let's see. Basically, it's gonna be like this: 1, 2, 3, followed by a huge jump. This is the fourth one, fourth, fifth. Okay, but for phosphorus, since phosphorus is in group 15, it's gonna be like 1, 2, 3, 4, 5. The sixth one should be a huge jump. Do you get it? So the fifth one isn't that high, but for aluminium, the jump occurs much earlier after the third IE. So logically, aluminium should have the higher fifth ionization energy. Understood? That's why the answer is A. Each of the chlorides listed is added to water, which forms a solution that reacts with sodium carbonate to produce carbon dioxide. So acids react with carbonates. So we need an acidic solution. Magnesium chloride forms an acidic solution. Magnesium chloride, silicon tetrachloride, SiCl4, and phosphorus pentachloride. Okay, so magnesium chloride does form a slightly acidic solution like 6.5, but it isn't acidic enough to react with sodium carbonate. Okay, that's why we're going to skip 2, but these two are really acidic, so they're going to form a very acidic solution which will react with sodium carbonate. So it's going to be 1, 3, and 4 clearly. 20. NaH is added to separate samples of magnesium chloride and barium chloride solutions. H2SO4 is then added slowly to each reaction mixture until in excess. What is observed at the end? So for barium chloride with NaOH, we're going to get barium sulfate, which is a white precipitate. It can't be colorless. Okay. But for magnesium chloride, magnesium sulfate is actually soluble in water. That's why it's a colorless solution. Okay. 21. 4 gram sample of anhydrous group 2 metal nitrate is heated strongly until there is no further change of mass. A solid residue of mass 1.37 grams is formed. Which metal is present in Z? Okay, let's try trial and error. So we have a group 2 metal nitrate, XCO3. Oh, nitrate, right? Sorry. Two, two, 4 and a 2, O2. So this is 4 grams. This is 1.37 grams. So we got to check this, okay? So what if we had barium nitrate? Do we end up with this? Let's see. Barium has an AR of 137.3. 137.3. So 4 divided by 137.3 plus nitrate is 14 plus 16 plus 16 plus 16. 62 times 2. 124. So 124 plus 137.3. 4 divided by answer gives us an answer of 0.0153. 0.0153 moles. This should also be 0.0153 moles. Multiplied by the MR, which is 137.3 plus 16, gives us an answer of 2.35 grams, which does not match with this. Next one, calcium. CaNO3 calcium oxide. Calcium is 40.1, I guess. 40.1. So 4 divided by 40.1 plus 124. This has 0.024375 moles. This is also 0.024375 moles. Multiplied by the MR, 40.1 plus 16 gives us an answer of 1.37. We got a winner. The answer is B. 22. Chlorine is bubbled through a cylinder containing aqueous sodium iodide and an immiscible layer of hexane. As the bubbles pass through the cylinder, what is observed in the lower and upper layers? Chlorine, it passes through sodium iodide. Chlorine can actually displace sodium iodide, to form NaCl, and iodine will be liberated. So the iodide layer, the lower layer, we'll see iodine color, the color of iodine, iodine color. That's really funny. So basically it was colorless initially, but now the solution will actually turn brown. Okay, so 22 is between A and B. What about the hexane? Hexane is actually an organic solvent. Do you understand? Hexane is an organic solvent. When hexane comes, like we actually use hexane to dissolve halogens. We get a purple color with iodine. We get a we get an orange color with bromine, and we get a yellow or greenish color with chlorine. So A is in fact correct. Okay. So we did use that. It is colorless in general, but it turns colored. It turns into the color of chlorine, basically pale yellow green. 23, 22A. 23. Chlorine and bromine have different volatilities. Which row identifies the more volatile of the two elements and gives the correct explanation? So chlorine is more volatile, clearly. Why? Chlorine is above in the group, so it has lower number of electrons. So the intermolecular force is weaker in chlorine. So the intermolecular force is greater in bromine compared to chlorine. That looks good. 24. Ammonium chloride dissolves readily in water. Which statement about the colorless solution formed is correct? Ammonium chloride. Ions in the solution can form hydrogen bonds with water molecules. This is wrong. In a sense. In a sense. Like you'd be confused at first. Because typically you'd be thinking about ammonia, right? I'm going to tell you the trick though. Look at the other ones. The solution is slightly basic. This is wrong. It is actually acidic. Ammonium is acidic. The solution will smell of chlorine. Basically, when it dissolves in water, ammonium chloride, it forms NH4 plus and chloride. So if you dissolve common salt, sodium chloride in water, does it smell of chlorine? It doesn't, right? It's wrong. When sodium hydroxide is added, when base is added to ammonium salt, basically a gas evolves which turns a red litmus paper blue. Okay, so D is also wrong. Why is it A? Ions in the solution can form hydrogen bonds with water molecules. Basically, when ammonium chloride dissolves in water, we get chloride and ammonium ions. Ammonium doesn't have a lone pair, okay? Ammonium doesn't have a lone pair. But here's the thing. When you dissolve ammonia in water, aqueous ammonia basically, what happens? NH3 actually accepts the protons present in water and it turns into ammonium, right? This is what happens when ammonia is added to water and we get the compound ammonium hydroxide. That's why the solution turns basic. So when you add ammonium chloride to water, do you know what happens? Basically the ammonium ions, they release protons and we also end up with ammonia which can form hydrogen bonds with water. That is why A is the correct answer. Okay, 25. At 550 degrees Celsius, nitrogen dioxide reacts with unburnt hydrocarbon fragments such as CH3 in the catalytic converter of a motor vehicle. Which row gives the energy change for this reaction and a proper reason for it? This might be a common MCQ, I've seen this. The reaction change is endothermic. Chemical energy is converted to heat energy. Is endothermic? The nitrogen triple bond is very high, but the nitrogen triple bond isn't being broken. Right, this is wrong because it's not being broken, it's being made, so it would support the exothermic part, right? That's why B is wrong. C, exothermic, because CO2 and H2 have negative del H formation values. Exothermic because double bonds are broken in NO2. Similarly, this doesn't help it because if double bonds are broken in NO2 it would be endothermic. It's between A and C. Endothermic, chemical energy is converted to heat energy. This doesn't support the reaction being endothermic. Any reaction which reduces heat is supposed to be exothermic. This is actually an exothermic reaction because it occurs in the motor vehicle, right? In the exhaust. So it should be C. It's an exothermic reaction for sure. And yeah, CO2 and H2 have a negative del F, HF values because bonds are formed which releases a lot of heat. 26. Compound X contains an alcohol group and a carbonyl group. Which row is correct? This type of alcohol is actually tertiary. Okay, and what is the type of carbonyl group? This is a ketone. So 26 is actually D. Okay, and aldehyde looks like this. 27. The diagram shows a skeletal formula of phenazine. Where's the empirical formula of phenazine? How many carbons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So C12. What about nitrogens? N2. So C12, N2 for now. Next, how many hydrogens? So remember, any double bonded carbon in a ring can bind to one hydrogen. So one hydrogen, two hydrogen, three hydrogen, four hydrogen. These already have four bonds. This also has four bonds. This one also has four bonds. So we have 1, 2, 3, 4, 5, 6, 7, 8. H8. So if we reduce it, C6NH4. C6NH4. I'm going to go with 27A, which is the answer. 28. The diagram shows the structure formula of mevalonic acid. Which reagent and conditions will react with mevalonic acid to produce an organic compound without a chiral carbon? So our compound over here does have a chiral compound over here, right? This carbon is chiral. So we somehow need to get rid of this. So basically what we can do is we can either oxidize the alcohol or eliminate it. So basically PCl5 isn't the correct answer because we'd get a halogen alkane. We'd still have a chiral carbon. Na at room temperature, that isn't fine because if you add sodium, it's basically gonna turn into O minus Na plus. It would still be chiral. So sodium isn't the correct answer either. Heat under reflux with potassium dichromate. A is wrong because it would form an ester over here. Okay, that doesn't help. But heating this would actually convert this to uh, you know a ketone. Would convert this to a ketone. So yeah, that's that. It's no longer chiral. 29. Structure and stereoisomerism should be considered when answering this question. All right. 29. Structure isomerism and stereoisomerism should be considered when answering this question. Y is a gaseous hydrocarbon which decolorizes aqueous bromine. Okay, that means it's an alkene. 10 grams of Y occupies a volume of 3.43 dm cube under room conditions. It's a gaseous hydrocarbon. So remember, gaseous hydrocarbons are till C3. From C4 onwards, it's a liquid. So till propane and propene, these are. So we can find out the moles of this actually. So I'm thinking I think it might be propene. So CH3, CH2, 10 grams, right? We can find out the moles really. 3.43 dm cube by 24. How much is that? 3.43 by 24 is 0.143 moles. Okay, so it needs to match with 0.143. Let's find out the MR of this. 12 times 3 plus 3 plus 1 plus 2, that's 42. 10 divided by 42. 10 by 42 is 0.238. Okay, so it doesn't cut it. Okay, it might be okay, so for alkenes it might be greater. It might be, you know, C3, CH2, CH, CH2 might be this. Let's find out the MR. 12 times 4 plus 3 plus 2 plus 1 plus 2. That's 56. So 10 by 56. That is 0.179. Still doesn't match. So it has to be greater. It's to be CH3, CH2, CH2, CH, CH2. Okay. So 12 times 5 plus 3 plus 2 plus 2 plus 1 plus 2. 70. 10 by 70 is 0.143. Matches. So it might be pent 1 in or pent 2 in. Might be pent 1 in or pent 2 in. or some other compounds, right? So we are dealing with pentene in general. We're dealing with pentene over here. You have to figure that out. So these are the possibilities: CH3, CH2, CH2, CH, CH2, or it can be. This has no cis trans isomerism, by the way. So we can branch out this chain. It was originally, it was like this, right? So maybe we can go for CH3, CH3, CH2. This is a possibility. No cis trans though. What about this? We can go for CH3, CH2, CH, CH, CH3. This is pentuene. Pentuene has, these have only one isomer. This one has two isomers. Then we can go for this. Okay. CH3, CH3. This is another one. So what's the isomer that we've missed? Basically, we have 2, 3, 4, 5 now. There's another one. Basically, if we draw it like this, it will make sense. Here you go. This is pentuene, right? In pentuene. So the one on the left, top left, is pent one in. Then the next one is 2-methyl butene, alright? Then this is one of the isomers. The last one is actually an isomer of the first one. This one over here. What if we kept it like this, CH2, and we completed the branching here? What if instead of CH3, CH2, CH2, I wrote CH, CH3, CH3. This has no cis trans isomerism, but this is another isomer. So in total, 2, 3, 4, 5, 6. There are 6 possible isomers. 30. Limonene is found in lemons and orange oils. What is the major product when limonene reacts with excess dry hydrogen chloride? Okay, so chlorine will go to the carbon with more alkyl groups, being this one, chlorine, and here it will go to this one, chlorine. So I'm looking for this compound. So 30 is actually C. 31. Which state? So always remember, for electrophilic addition reactions, if we add HCl or something, the chlorine or HBr, the bromine will go to the carbon with more alkyl groups involved in double bonding. Okay. 31. Which statement concerning the hydrolysis of 1 bromopropane with water is correct? Okay. Hydrolysis reaction between water and 1 iodopropane is faster. That is true, because the CBr bond is less polar than the Ci bond. This is not the correct answer. It's because of the... No. The C-Br bond is actually more polar, and the bond length of Ci is longer. That's the reason. B. The A is wrong. The hydrolysis reaction with water is very slow because water is a weak electrophile. So electrophile does nothing here. This is actually a nucleophilic substitution reaction. This is also wrong. It's a weak nucleophile. The mechanism of reaction involves the formation of a stable carbocation. Since it's a primary halogen alkane, we do not get a stable carbocation. We get a stable carbocation if it was a tertiary halogen alkane. But here we get an unstable intermediate. If it was tertiary, 3 would be correct. The reaction is slower with 1-chlorpropane because Cl bond is stronger than Cbr. Now this makes sense. 31 is D. Compound J, C15H2 and 3Br2Cl, is reacted with an excess of hot concentrated solution of sodium hydroxide in ethanol. So an elimination reaction will occur. One of the products is X. What could be the skeletal formula of X? Okay. So basically you guys need to understand that due to elimination it can either be this or this, but the one on the right is not possible because then this carbon would have 5 bonds. That's not possible. So my bad. Bromine, basically after elimination the double bond must form here. Do you understand? So this is excluded. The double bond must form down here. So A is a candidate, B is not a candidate, C can't be possible, D is a candidate if I'm just looking at this bond over here. Okay, next we have this bond in the first place. Yeah, so for chlorine there are two possibilities. We might either get this one or this one, or you know what, even this one. But actually this one isn't possible because then this bromine couldn't go here and it would form a bond here, right? And this never happens. The two double bonds are never adjacent to each other. Please remember that in a cyclic compound this isn't possible. So chlorine can't actually get here. It's either there or there, and bromine would have to go here then. This is the only possibility. So we are looking for bromine over here and chlorine over here or here. Which compound matches with that? 32 is A, here and here. That's the reason. Okay, so we got rid of this and got this bond here. We got rid of this, got this bond here. Got rid of this, got a bond here. 33. Structure isomerism only should be considered when answering this question. Several compounds with molecular formula C4H8O2 have one carbonyl and one OH group. Okay. How many of these compounds produce yellow crystals with alkaline iodine at room temperature? Okay. We should only consider structure isomerism. C4H8O2. One carbonyl and one OH group. Alright. So basically it can be like this: CH3, CO, CH2, CH2OH. This is a methyl ketone. It can form, it can give a positive result. Okay, so we got one. Moving on. Does this match, by the way? C4, 1 2 3 4, oxygen 2, hydrogen 1 2 3 4 5 6 7 8. Okay, what about the next one? We can have this CH3, CO, CHOH, CH3. This can also give a positive result. This is possible. Okay, so we got a 1 2. What about if we have what if we have a secondary alcohol? We might have this compound CH3 CHOH, right? Then we can go for CH2 CHO. We can have an aldehyde, right? We can have an aldehyde but a secondary alcohol. This can get oxidized to a methyl ketone, which will give a positive result. Do you guys understand? So yeah, that's more or less it. So the answer should be 3. 3 is B. Pentaerythritol is used as an intermediate in the manufacture of paint. Pentaerythritol. Okay, so I thought it had something to do with erythrocytes, but it's pentaerythritol. Pentaerythritol. It can be dehydrated by concentrated sulfuric acid to form an alkene. That's wrong because to be dehydrated you do need an alcohol group, but you also need a carbon adjacent to it with a hydrogen. Since this carbon does not have hydrogen, that is actually not possible. So A is wrong. The empirical formula and molecular formula are different. Let's check. This is C5H4 1 2 3 4 1 2 3 4 5 6 7 8 9 10 11 12 H12O4. Actually no, this is the simplest state. Pentaerythritol does not react with acephate, potassium manganate. This is wrong. These are all primary alcohols. We can get this compound, right? No one's stopping us. Okay. 1 mole of pentaerythritol gives 2 moles of hydrogen gas on reaction with excess sodium. Okay. So for each alcohol group, we're going to get 1 mole of hydrogen atoms. 1 mole of hydrogen atom, 1 mole of hydrogen atom, 1 mole of hydrogen atom. So in total, 4 moles of hydrogen atoms or 2 moles of hydrogen molecules. So yeah, D is correct. 34 is D. So remember that. Like carboxylic acids and alcohols, they react with sodium to give 1 mole of hydrogen atoms or half moles of hydrogen gas. 35. Which reaction has a nucleophilic addition mechanism and gives a good yield of product under the stated conditions? No, this is elimination. This is wrong. 2-iodopropane with hot aqueous sodium hydroxide. This is all right. This is so. Oh wait, this is elimination. 2 is nucleophilic substitution. Okay, it's not nucleophilic addition. Nucleophilic addition, like carbonyl compounds undergo nucleophilic addition. Okay. Now, what's the condition though? Propanol reacting with HCN under alkaline conditions and propanol reacting with HCN under acidic conditions. So basically, we require, suppose if we require propanol, CH3, CH2, CHO. So basically, going to react with HCN under the presence of a catalyst KCN. Okay, we need potassium cyanide. So what is KCN? It's the salt of a strong base. KCN is the salt of a strong base. Basically, it's the salt of potassium hydroxide. Potassium hydroxide is strong base, and this is the salt. So strongs, salts of strong bases are actually weak acids. When you actually, why is KCN given? When you react it with water, it actually produces the strong base KOH and it liberates cyanide ions. So it actually acts as a source of cyanide ions which act as the nucleophile which attack the CHO on propanol. So to get maximum yield, we actually need alkaline conditions. So the correct answer is C. This will give us maximum yield. It's not acidic, okay? The KCN added actually provides an alkaline solution. This isn't usually taught, but KCN is the catalyst, but when you add it to the solution, it becomes alkaline. A carbonyl compound has a structure formula CH3 CO CHO. So it will react with 2,4-DNPH to give an orange PPT, and it will react with Fehling's to give. So Tollens gives a silver mirror, and Fehling's gives a red precipitate. So 36 should definitely be D. An ester is shown. Which two compounds react to form this ester? Break the bond. The ester breaks here. So this left part is the acid actually. This is an acid with 3 carbon atoms, so it's basically propanoic acid. Clear? It is propanoic acid. And what about the alcohol over here? It's an alcohol with 1, 2, 3 carbons in the main chain. Okay, so it's mainly propanol, but it's propan-2-ol actually. It's propan-2-ol, but there's a methyl group on the second carbon, so it's 2-methyl propan 2-ol, 2-methyl propan 2-ol. That is why the answer is B. 37 is B. 38. Which compound can be used to make can be used to make propanoic acid by treatment with a single reagent? Okay, so basically with a single reagent, how can we make propanoic acid? Acid hydrolysis of this results in butanoic acid because it has 4 carbons. What about this compound? If you add hot KMnO4, it will cause lysis of this bond, and you're gonna get carbon dioxide and water on that side and propanoic acid on the right hand side, because the carbon attached to the double bond has one alkyl group. So we get a carboxylic acid, which is CH3 CH2 COH. Get it? So the answer is A. Great. 39. A sample of sulfur consists mostly of 32S. It also contains 4.2% sulfur 34 and 2.8% sulfur 36. What is the relative atomic mass of this sample of sulfur? Okay, so let's find out the percentage of 32S. That's 100 minus 4.2 minus 2.8. That gives us 93% of this. So 0.93 times 32, okay, plus 4.2 by 100 is 0.042. 0.042 times 34 plus 0.028 times 36. Okay, so do this 0.93 into 32 plus 0.042 times 34 plus 0.028 times 36 gives us an answer of 32.196. So which is rounded off to 32.2. We're going to go for B. Typically it's 32.1, but for this sample it's 32.2. One molecule of an addition polymer containing 200 repeat units has an MR of 112K, 112,000. The polymer molecule contains chiral centers. What is a possible monomer for this polymer? Okay, so for A, it's CH2, CH, CH3, followed by CH, CH3, like this. So basically, to get a chiral compound, we need different atoms, 4 different atoms attached to one carbon. Okay, for example, this is a no-go. Clearly 40B is a no-go. Why? Because the same atoms are attached to this. Like it would be like this: CH, C, CH3, CH3, so there was no hope of getting a chiral carbon. So B is eliminated. It's between A, C and D. Now it contains 200 repeat units. All right, and the MR is this. So let's find out the MR of these compounds. So 12 plus 12 plus 12 plus 2 plus 3 plus 1. That gives us a value of 42. So 42 times 2000 gives us a value of 84K. Okay, okay, so that doesn't match. What about C though? C is 12 plus 12 plus 12 plus 12 plus 2 plus 1 plus 2 plus 3. That's the mass of one monomer. 56 times 2000 is actually 112000. So we are gonna go with C. All right, so that's that. So this was also 56, but it didn't fit the criteria of containing chiral centers. That's why we excluded B and C is the answer. Okay, guys, hopefully that made sense. Hopefully that helped you. So that's all for today. I'm gonna link the paper for May June 2022. Paper 1-2 up here, and the paper for May June 2022. Paper 1-3. Sorry, this is 1-3, right? Okay, so I'm gonna link the paper for May June 2022. Paper 1-1 up here, and the paper for May June 2022. Paper 1-2 down here, right? And the playlist for paper 1 up here. And if you like the video, remember to subscribe to the channel and share the video with your friends. See you. Also, I'm going to be solving paper 2 next, so keep your eyes on the channel.